So, then welcome to lecture number 7 in the winter semester 24-25. Today we go, okay, people are coming. Today we go to some practical things, initial and boundary conditions. Unfortunately, we cannot cover really everything necessary there. We don't have pressure boundary conditions in this lecture. We always need more time to cover everything. But I think this is normal for a lecture. In a lecture, you only learn, part of stuff, and later you will have, if you study it further, you'll have to catch up a little bit with the books. Okay, initial and boundary conditions, but in addition to this, we also cover the scaling of physical units. And this is what we are going to start with. So this is something very necessary. Scaling of units. So usually we have given, what's that? We have a given delta x that is in meter, and we have a given delta t which has the unit seconds. And what you want to find is a mapping. Something is wrong with my pen today. Mapping from physical velocity. So we put the physical velocity with the star and pressure P star, so this is the physical. Usually we also want to find how to adjust the viscosity. This I leave to you a little bit. This is similar to velocity, scaling velocity. This is something I leave to you as an exercise. Remember, viscosity is given in the units delta t squared by delta x squared by delta t, because it's a diffusion, yeah? And this you have to scale similar to the velocity, and I encourage you to do this as an homework. Could also be a question in the exam, yeah? So, okay, we have a mapping of velocity and pressure and to lattice density. Not the density of the lattice nodes, but the density rho that we use in the Lattice Boltzmann method, because this is what we use as a replacement for the pressure. It comes a little bit from kinetic theory. What am I doing? Okay, so lattice velocity u, this is the thing without star, is always given in delta x by delta t. So with lattice velocity, we mean the velocity that you set in your Lattice Boltzmann methods. Yeah, I worked together with a postdoc for some time who I introduced to Lattice Boltzmann, and then his code never worked, and we spent weeks looking for the mistake, and then suddenly I noticed that he used physical units in his velocity, which I just didn't assume that he would do something like this, yeah. But even though you can talk to people for a very long time and you see you missed a very simple fact. Yeah. So you never use physical units in Lattice Boltzmann. I encourage you not to use physical units in finite elements too. Yeah, but if you do this in finite elements, at least it will work. In Lattice Boltzmann, it will simply not work. You have to use these lattice units. Velocities must be given in delta x by delta t. Viscosity must be given in delta x squared by delta t. Yeah, otherwise it doesn't work. No physical units here. So this is the lattice velocity. Yeah, and we get the lattice momentum, of course, by taking the sum over I, so in 2 dimensions. Yeah, say we have here, this is a vector with I and j, Fij delta x by delta t. And you know, when we program things, we usually skip over delta x and delta t. These things are considered to be the units, so we just don't use them. So when you have now the scaling, this is pretty simple actually. Scaling, so this is the Lattice Boltzmann unit. This is the physical unit. As it's the same as velocity, you just want to put it in a different units. And now what you do is you multiply this by delta t and divide this by delta x, writing this in red, and then you multiply this again by delta x and divide this by delta t. And what you do is you will keep this as the new units, and you will replace this, or you will insert the numbers for these things. Yeah? So if this was not clear, then let's try to do this with an example. So example, say we have delta x, the resolution of our grid is 1 millimeter, say, and delta t, the resolution of our time step, is 1 microsecond. And say we want to set a velocity of 0.1 meters per second. So this is the physical velocity, and this is translated now into u. So u is the value here, 1 meter per second. Then we introduce, then we insert, yeah, the red one. So we multiply by delta t and divide by delta x, which is the inverse of the units. Yeah, so this is, we have, what is it? 10 by the power of minus 6 seconds divided by, what was this? 10 by the power of minus 3 meter. Yeah? And then we leave there delta x by delta t. Now you see that the units, meters and seconds, will disappear. Yeah? And you just have this factor, and you end up with 10 by the power of minus 4 delta, by minus 4 delta x by delta t. Okay? So it is 3 through the units, and it is 1 through 0.1. Yeah? So this is how you translate the velocity, and hopefully this should make it clear how you translate the viscosity too. Yeah. So there's one thing that's a bit out of line here probably. That's the lattice pressure. Which I should try to write correctly. Lattice pressure. So actually we could talk about pressure. I think pressure in Lattice Boltzmann is not sufficiently well understood in general. Yeah, but we'll keep it simple and stick to the usual view. So in Lattice Boltzmann, okay, let's say actually the pressure is the second moment. Yeah, it's the trace of the second moment. That's the actual physical pressure. However, in Lattice Boltzmann, this trace of the second moment is by means of the equilibrium always related to the zero moment. Because we have a fixed temperature. Yeah? Yeah, because we have a fixed temperature, the pressure only depends on the density. And this is in the physical world also the case, given you have your temperature, then pressure depends on density, yeah, by an equation of state. And so this is why we usually use the zero moment as indicator of the pressure and not the second moment as indicator of the pressure. There is, of course, this small difference that they will be equivalent only in equilibrium, and the second moment is not necessarily in equilibrium. And so there is a small difference between these two things, which you can actually see that it makes a difference whether you consider the one as the pressure or the other, but you know, this is an advanced topic. If you want to write a thesis about this, yeah, you are welcome. Pressure in LB is expressed by an equation of state. So there's the ideal gas law, basically P. Physical P is related to the physical rho times the speed of sound square. Yeah, this is because the speed of sound square is the Gauss constant times the temperature, and rho is the mass of the particles by, or the mass by the volume. Yeah, so mass of the particles. Yeah. So, yeah, this comes a little bit from kinetic theory. The Navier-Stokes equation is a little bit different. In the Navier-Stokes equation, the pressure is a potential, and we don't care where it's coming from. And as a potential, you know how potentials work. They're only relative. Right? So you only care about in the gradients, so you only care about differences in pressure, which is why in the Navier-Stokes equation, and this is another problem that newbies could run into when they implement and have, I mean, I've observed this many times actually. When they deal with Lattice Boltzmann in the Navier-Stokes equation, you could say that the background pressure is zero, yeah, because pressure is a potential, so you don't care about where your level of your potential is, right? Where your what is it? The reference is, yeah. Now we come a little bit from kinetic theory, and in kinetic theory, if pressure is zero, you are in a vacuum. Right? So there is no, so if you initialize your pressure in Lattice Boltzmann with zero, because this is what you do in your Navier-Stokes solver, crash. Yeah? That doesn't work. Okay, so what are we doing? We have a fixed temperature, so what we are doing is we say that we take a relation between the pressure and some zero pressure, normal pressure, I don't know, and relate this, so their ratio is equal to the density in lattice Boltzmann and the reference density. Yes?
This equation for the pressure in terms of the density comes from the ideal gas.
This is ideal gas equation. Yeah, so we usually use the ideal gas equation, and this is there are in multi-phase flows there are some other possibilities. Yeah, so where you have a non-ideal equation of state that, for example, helps you to get agglomeration of building droplets or something. But this is always a bit, all of this is not very physically correct. So there's a lot that you have to care about here. Yeah. So if you, it's not the topic of this lecture here. So we have a reference density. And this reference density can be set, in order to make things simple, rho 0, we can set this to 1 so that we can say that our density would be the physical pressure divided by a reference pressure. So how does this look like? Going to the generic example where you deal with pressure-driven flow. Example, so we have a pipe. And in this pipe, let me see that I don't mess this up. In this pipe, we have a pressure on one side and we have another pressure on the other side. And we have to specify a density on one side and a density on the other side. And let's say the difference in pressure, which is of course P1 minus P2, yeah? So say this is 100 Pascal, as an example. And say our background pressure, okay, suppose we are in air, right? Suppose we are in air, then we'll have, for example, 1,000 hectopascal, so it's the 10 by the power of 5 Pascal. So let's say at the output, okay, say flow is supposed to go this way. Say we have the outlet back here, this doesn't matter, but say this is the outlet, so we'll put this to the reference, so we put this to 1, this density to 1. Then rho 1 by rho 0, which is 1, is now this difference plus, okay, so basically this is P2, yeah, divided by the reference, say the reference, okay, let's say P, right, no, it doesn't, no, sorry. Okay, this is already what I wanted to say. Yeah, so it's the difference, so it's then P2, yeah, and you see this is now 1 per mil larger than the reference pressure. Yeah? So this is how you can set a pressure difference. I have been cited by somebody, I don't know whether I ever said this, but I have been cited by somebody saying that pressure is one of the lower gods in the religion of the Lattice Boltzmann method. For whatever reason, people in the Lattice Boltzmann world, we try to avoid pressure. Okay. Next topic, unless you have any questions. Initial conditions. So, initial conditions is again a little bit different from the Navier-Stokes equation, insofar as we need initial conditions for all the moments. Okay, now triviality. We said there are many moments, yeah? So we have hydrodynamic moments, we have ghost moments, and we have alien moments. Do we need initial conditions for the ghost moments? Yes. No?
I would say no.
No?
For the ghost.
For the ghost. So how do you, how do you actually do it if you don't have initial conditions for the ghosts?
Well, in that case, yes.
You have to set something, yeah? You have to put there something, yeah? So, okay, but how about the aliens?
I would say, so the aliens are the ones that you need. So, for example, for the, I'm just trying to see if I understand, but
Yeah.
for the D3Q, let's say 15, the aliens would be these 15, and the ghost would be the...
No. The 15 are not the aliens.
They're the ghosts.
Well, you need 10 hydrodynamic moments, right? So when you have D3Q15, then 10 of them are hydrodynamic.
Okay.
Then there are 5 on top of this, and these are ghosts.
Mm-hmm.
And then there is infinite many aliens.
Mm-hmm. Okay.
So the aliens are, of course, these that are automatically set if you set the hydrodynamic and the ghost moments. Yeah? But you cannot just set the hydrodynamic moments as you would in the Navier-Stokes equation. But you have to, even if you don't think about it, yeah, you have to do it because you actually set them. Yeah. So for all the moments, that you actually have, though in your example where you talked about D3Q15, you would have to set 15 initial conditions. So this is different from the Navier-Stokes equation, which actually, so there are 10 hydrodynamic moments. How many initial conditions do you need for the Navier-Stokes equation per point in space? Do you need all 10?
You would need for each node.
Yeah.
We would need one initial, or for the velocity, we would need a condition.
Yeah, and what else?
And we would also need for the pressure.
Yes, so these are 4.
Okay.
Yeah, so this is interesting that you don't even need initial conditions for all the hydrodynamic moments, because the Navier-Stokes equation works in a different way. The hydrodynamic moments, part of them are the stresses, and the stresses can be, the stresses are given by the velocity fields gradients. Yeah, so all you need in the Navier-Stokes equation as initialization is U and P, nothing else. Now in kinetic theory, you need more, and in Lattice Boltzmann you need more. You need all the moments. So what are your options? Do you have any proposition that how would you do it? How do you usually do it?
We would need a density, which would be the zero moment
Yeah.
condition for the zero moment.
Now, yeah, okay. How do you specify your populations?
Well, with the
okay, we get something from the internet. So no.
Yeah, I was gonna say that Gaussian distribution,
Gaussian
like based on the velocities
the
that
Gaussian
we have.
distribution, yes, the Gaussian distribution is of course their equilibrium, right?
Yes.
So you would initialize with the equilibrium. So
No,
this
like
is okay. So that would be the equilibrium method. The equilibrium method. This is very popular. So, as you just said, you need velocity field x, and so x and time t, time 0, and you have a density field on x and time 0. Yeah. So, given these, you very simple compute the Gaussian, which is, of course, the local equilibrium. Actually, we call it the Maxwellian. It is a Gaussian, yeah, but we'll in kinetic theory we call this the Maxwellian, not the Gaussian. Yeah, Gaussian is the same thing, just in a different context. Fij equilibrium, given velocity and given density. Yeah, from Gaussian, but I'll write Maxwellian. From the Maxwell, or from the Maxwell moments. You could say the Maxwell distribution. So, this is actually done because, mostly because it is simple and because, you know, we are engineers, it works. So it's simple and it works, but it is wrong. Yeah? So it is wrong because second, moments are wrong. So not always, but in the case that the initial conditions has any gradients. So there are gradients, then it's wrong. What is the consequence out of this? The consequence is that we have wrong dissipation. So the viscosity is not what you expect it to be. Wrong dissipation in the initial phase. You see, there are many cases where you don't actually care about the initial condition. Yeah? So you set any random initial condition and then you let it run for long enough. Yeah? And then what was initially set doesn't matter anymore. Okay? So in this case, you simply initialize with equilibrium, you let it run for long enough, and then you are good. Of course, if you are interested in what happens in time, right after you started the simulation, for example, you have a specific setup and you want to see what happens yeah, when the flow condition is such and such, what happens next? Yeah, so then you can't do this. Yeah, you cannot do weather forecast or something like this, where you have, okay, this is my initial condition, and we want to see how it's going onward from here. Yeah, then it doesn't work. So for this, we need to have at least second moment non-equilibrium initialization. And this is where actually our knowledge on asymptotic analysis comes now handy. So let's remember what we have learned in all our theory sessions so far. The Navier-Stokes limit. This is the thing that we want to solve. Requires the second order moments to be second order consistent. Remember, I don't know why I can't. Yeah, remember how we arrived in diffusive scaling with delta x being our smallness parameters. Yeah, we needed the second order moments to second order, and we needed the third order moments to first order. So this means we have to look in, if we want to solve the Navier-Stokes equation, we have to look up what are our second moments. So with the overbar to second order. So this is, now you can look up in last lecture, this is the equilibrium to second order minus 1 over omega minus 1/2, and here comes 2/3 dx ux to first order, and this times the density to zero order. And by this, I already used that to second order, the divergence will disappear. Yeah, this is already included in this equation. So the other two second order moments look like this, very simple. M0 to equilibrium to second order minus 1 over omega minus 1/2. It's basically the same, 2/3 dy now times dy of uy. This with rho zero order. And the last one that we have in 2 dimensions is M11. This is M11 equilibrium to second order minus 1 over omega minus 1/2. Here comes, here comes 1/3. I write 1/3 in front. 1/3 dx uy to first order plus dy ux to first order, and this times rho to zero order. So they are required to second order. The third order moments you know, it's a bit annoying that there are two things that are called order: the order of the moment and the order of the, I mean, third order moments to first order is a bit confusing, I guess. Yeah, I'm sorry for this. Well, I mean, this is how they are called. Okay, M12 is to first order a third row 0 order times ux first order. There is no non-equilibrium part here. Yeah, you remember the non-equilibrium part includes the collision operator omega. Yeah, and we derived last time that omega 0 order and omega second order is always 0. Yeah, so if you ask for a moment in first order, it will always be its equilibrium, and only the first order part of its equilibrium, of course. Yeah. So right. So this basically means that this is the first order part of its equilibrium, and same thing, of course, for the other third order moment that we have here, 1/3 row 0 uy first order, which is then again the equilibrium to first order. So this means, so this is that you have to do, that we need in order to get the thing being consistent with the Navier-Stokes equation. So as an initial condition for second moments now in pre-collision form, I mean, this is how you usually, yeah, by the way, right. You cannot set as the initial condition, you cannot set m over bar, obviously, yeah? Because m over bar is what you have in between pre and post collision. Yeah, you have to set either the post collision or the pre collision. Usually you set the pre collision and then you do a collision and then a streaming. Yeah, so then we have to specify the pre collision, and the other thing is you cannot specify things to a certain order. This is something that comes out of the analysis. Yeah, you have to set actually the moment. You only have to guarantee that it is 2 second order equivalent to this equation up here. So in practice, of course, you cannot control m 2 second order, because this would be the actual solution to the Navier-Stokes equation without the errors. Yeah. In reality, of course, you always have error terms. You just guarantee that they are small enough. So then it's M20 in your initial condition would be M20 equilibrium minus. So in the M over bar version, we have here 1 over omega minus 1/2. Yeah? In the, I don't know whether, probably you don't know by heart. No, maybe not. What would it be? 1 over omega. Okay, you know by heart. They're very good. Yeah. So the other one for the post collision would be 1 over omega minus 1. Yeah.
Yes.
Yeah, and for the pre collision is 1 over omega. So the average between them is 1 over omega minus 1/2. Yeah. So, but you said the pre collision, so it's 1 over omega rho 2/3, and here comes your dx ux. So if you have a gradient in velocity, yeah, so you have to specify this in your initial condition. M02 is M02 equilibrium minus 1 over omega rho 2/3 dy uy, and M11 is M11 equilibrium minus, so wait, we have, in this we have a third, okay, maybe I should write this the other way around, but okay, we have 1/3 times 1 over omega times rho, and then comes the dx uy plus dy ux. Okay. Is this clear?
Yes.
Okay. So the others, the third order moments and all the rest, the rest, basically these here are the corrections, and all the rest you could do with equilibrium. Yeah. So you said third order to equilibrium, but you have to specify this to be consistent with the solution of the Navier-Stokes equation. Okay. Now coming to boundary conditions, and as I said, we'll skip over pressure boundary conditions. What's that? Gehobene Hand.
I raised my hand. Can I ask
You raised your
something?
hand. Yes. Wait. I have to increase.
Yeah, no worries.
So okay. Maybe I hear you better now. Please.
Okay, so my question is that I don't, like in the beginning, I don't have the solution. So, but how would I know the gradient of u of x?
Okay, so now you have the solution. You have to specify a velocity field, right?
Yes.
This is what your initial condition is. So now.
But usually, isn't it like everywhere uniform?
Yeah. So if it's everywhere uniform, I mean, you said this is usual. I don't know. It depends on what you want to do. So if it's everywhere uniform, then your gradients are 0, and you can initialize with equilibrium. Yeah. So then there is, suppose you want to study a certain wave. Yeah. So then you initialize your wave, right? So the wave is not everywhere uniform, obviously. So you will have gradients, and now you have to specify this. So basically, I mean, you will have some function that specifies your initial condition. And this function, you have to compute the derivatives of this function, yeah, in order to compute the stresses that we have here. And then you have to set the stresses in the initial condition of the second moment. Yeah?
I see.
Yeah, clear?
Yes.
Okay, so then we continue now with.
I also have a question.
Yeah.
For example, in the case of the driven cavity, there
Yeah.
we would have the gradient, and let's say that it's on the top, it has an x velocity. Then from here we see that the M2 would have this term. We would get this term different than 0, for example, right?
The lid-driven cavity is not the best example for this, because the lid-driven cavity you could easily start from 0.
But why can we start from 0? Because we mentioned.
I mean, why can you start? No, it really depends on what there's no general rule that you can start from 0. You can start from 0 when you're not interested in the, in the beginning of your simulation. Okay. So in the lid-driven cavity example, you are usually interested in the long time behavior of your flow. Yeah? So if you're interested in the long time behavior of the flow, you don't care how your flow actually started. So, but if you want to study, the wave, a certain wave form that is hitting your shoreline, say, yeah, so then the thing has a certain form. Yeah, and then you have to, if you want that this form is actually arriving, you have to adjust that particular form. And then you have to compute these gradients and set these gradients.
For example, for instabilities.
For instabilities.
That would be how to initialize
What do you mean by instabilities?
Or for example, the Rayleigh-Bernard convection, where you want to see how the...
Yeah, the Rayleigh-Bernard convection is also, there's, you know, there are some specific benchmarks. For example, a Taylor-Green vortex. So this is a certain vortex that you initialize, and you want to see how this is generating turbulence, how this is decaying. So there's one vortex, and this is decaying to many vortices. Yeah. So, and this, for example, only works if you initialize this with the correct initial condition. Yeah. Rayleigh-Bernard convection is not the because this is also something where you are interested in the long time behavior. Yeah, this is usually what I said. I mean, usually weather forecast is not done with the Lattice Boltzmann method a lot. But think about a weather forecast where you have some initial condition given, and you want to see what happens in the next 2 hours. Yeah. Then you're not interested in the long time climate thing. You're interested, this is your initial condition, what does this lead to? If this is your question, it's essential that you have the right initial conditions also for the non-equilibrium second moments. Okay. Yeah? You know, all of this always depends on what you want to do. Yeah? It's not... sometimes it's not of interest, sometimes it's very important. So let's come to the boundary condition. So we'll call boundary conditions BC. Here again, we are in trouble because the Navier-Stokes boundary condition, this is something that you know, I know some people who say we'll never do Lattice Boltzmann because we don't know what the boundary conditions are. So they cannot be imposed directly. Mathematicians hate us because we specify boundary conditions physically and not like, okay, this is a Dirichlet boundary condition or this is a Neumann boundary condition. It's actually something that in our worldview doesn't play a big role if this is Neumann or Dirichlet, or we look at this a little bit different. So what you have to do, I mean, you cannot specify fluxes or velocity or pressure or something, but what you have to do is you have to set boundary conditions for the populations. Yeah. And there are, let's say, 2 different concepts. The first one, we'll always start with the one that is less useful. That's more related to, you know, a little bit how the world looks like in the view of people who come from the Navier-Stokes equation. So they are the node-based boundary conditions, which is also called wet boundary conditions. Wet boundary conditions means that we put, it's another word for boundary conditions that you set on lattice nodes. And maybe if you come from any other field of numerics, you would probably set so boundary conditions at the nodes where else. Yeah. So basically, this is for some people this is very natural, and we may come to the point why in Lattice Boltzmann it is actually not. Yeah. So what we make use of a lot here is this characteristic diagram of the Lattice Boltzmann method that we've introduced 2 lectures ago, where we have a one-dimensional x direction and the t direction. Yeah, so we'll just look in one dimension because otherwise we cannot draw it. Yeah, and we have our lattice nodes like this, and they propagate in time and in space. And you remember there are these populations that move in this way. What am I doing? So, and let's say here we have a boundary. And, oh, before you draw it, let me draw this in a different color. So, now the problem is that this red population, also in the next time step, comes from outside. Yeah? So we don't notice. Now we have here, so the pre-collision population, so this is the pre-collision population at the wet node, yeah, that's coming in. This is the black one here. This is pre-collision. At BC, so BC is this location here. And we'll have a post-collision at BC. So call this thing here F, as always. In post-collision we call this F star. So how to deal with this thing? So there are kind of two approaches. That have been common. First is, replace all populations on the BC nodes. So for example, the different ways of doing this, but for example, you could set it with equilibrium. Now this is something, okay, I start with the very simple thing, right? So you could simply say, I have here the boundary nodes, and in every time step, for example, I want to have a certain velocity there, or a certain pressure there, or actually a certain velocity and a certain pressure. And I simply set the equilibrium given the certain velocity, given the given velocity and the pressure. I simply set them in every time step there, yeah. And you will actually see that this kind of works to some extent, say. Yeah. Then another way is that you replace only missing populations and you try to get some information out of the populations that were coming in. Because at the boundary we also have information that's coming in from the domain. Yeah? So this is here this black part. This is coming in. Yeah? So in particular, if you do this replacement of only missing populations, then it of course depends on what are your missing populations and what are the populations that you have. And this depends on the orientation of your boundary very, very obviously. So the node-based BCs depend on the orientation of the boundary. So this may be not a big problem if you say we can just turn it around. But sometimes you also have more complicated cases like corners. And also it depends on what lattice model you actually have, because these kind of boundary conditions are different for D3Q15 and D3 for Q19, obviously, yeah, because you have different missing different missing populations. Okay, so they are only for specific cases. Another thing is that they give you, of course, Legoland boundaries, because they have to be located at the nodes, obviously. So now the infamous example that you will always also find, unfortunately, in the book. And let me see at your face. So Suhe. Okay, people like Suhe boundary conditions. You know, Suhe boundary condition is from 1996, I guess. Okay, I guess there are two people present here that were alive at this time, and the others are potentially, I don't know from everybody, but most of you have not been younger than this boundary condition. So they did this. So they did it only for the 2D Q9 model. So, and so this is a wet boundary condition. It is, you find this in the book. Of course, I mean in several books, but in particular in the book that is very common. Yeah, and I find this a little bit unfortunate. I have something. I mean, I'm always bashing the book, but this is not really my. I mean, one thing that you have to say about the book is that the book is written by people who focus a lot on complex fluid stuff. Yeah, so this is their domain. They come from the complex fluid stuff, so simulating blood and these things, and usually these things have very low Reynolds number. It's very low Reynolds number flow. Yeah, so in this context, the Suhe boundary condition kind of works. If you belong to the domain of atmospheric flows, and I know that some of you are, yeah, or big external flows, atmospheric flows, flows on vehicles, yeah, Reynolds number in the excess of 1 million, 1 billion, then Suhe is an absolute no-go. It absolutely doesn't work. Okay, this is as a warning, but okay, let's look what it does. I mean, it's important to talk about it because if you look in any book or anything online, it's always okay. Do Suhe, yeah, for whatever reason. So, say we have a wet node like this, and we have a wall on the right side. Yeah, so then. Before you do the collision, and this is a wet boundary condition, this means you do a collision at the boundary, okay? So before collision, you have this F11, F10, and F1 minus 1. This is unknown. This is unknown because it would come from the left. Yeah? So what Suhe is now trying to do is to use the boundary condition, which is the given velocity, the given density. Yeah, so we have velocity and density and somehow, and get this information in order to recover with with the information that we actually have, that went in, and together with this, we want to recover the missing population such that on that node, we have exactly the given pressure and exactly, or not the given pressure, but exactly the given velocity. You can also rewrite it for pressure, for density, yeah? But usually it's in the original version, I believe, or they may have both in the same paper, I don't know. But what we usually mean is velocity boundary condition. Okay, now you have ux times rho, where you say that this is the sum over ij I fij, yeah? And this is, so I'm now using these brackets and I'm writing inside the brackets the guys that we don't know, yeah, just to isolate them. So these are the guys that we don't know, and these are the guys that we know. F. F0 and 0. Okay, I have some mistake in my notes, but I think this is correct now. Yeah. So 7.2. Okay, I will take over time today again, but I don't have to catch the train. So we have the y direction, j fij is equal to, now here we only have f11 minus f1 minus 1 plus f minus 1, 1 plus f01 minus f minus 1 minus 1 minus f0 minus 1. And I need a new page. 7.3. Rho is given as sum over ij. Of course not. Sorry. Fij is just the sum over all the populations, where we don't know f11 plus f10 plus f1 minus 1, and after this all the others, plus f minus 10 plus f1. I mean, this is a boundary condition from the time when actually Lattice Boltzmann was very poorly understood, and yeah, and they use concepts that are not. Okay, let's. I mean, I notice I have a little bit with this lecture, I always have the tendency of bashing things that I've not invented. Yeah. Yeah, so this belongs to the history of Lattice Boltzmann, of course. Yeah. So we put 7.1 and 7.3 together to get 7.4. So basically what we do is we replace what we don't know. Yeah, and what we don't know, so you see in 7.1 you have D3, the sum of D3, and you also have the sum of D3 in 7.3. Yeah, so you can equate these, yeah, in order to get to rho. So if you equate this will then eliminate all the unknowns. It will eliminate all the unknowns. Is equal to ux times rho plus f11 f minus 1 plus f minus 1, 0 plus f minus 1, 1. So of course you could not do anything with this if this was not on the boundary, right? So, but in the boundary you want to specify either ux or rho, right? So what now you can do is you can solve the thing. If you want to set in the boundary you want to set rho, then you can solve this for rho. If you want to set u, you can solve this. No, sorry. If you want to set rho, you can solve it for u, and if you want to set u, you can solve it for rho. Yeah. Then we need an additional condition, 7.5, which is very ad hoc actually. F10 minus F10 equilibrium. This is the one that we don't know, yeah, but we assume that we know the equilibrium, F10, and we also know F minus 10, and we also know the equilibrium of minus 10. So this condition here is called non-equilibrium bounce back. Basically, we assume that the non-equilibrium in these two populations is the same, which, if you analyze it, makes perfect sense. Yeah, but I find it still a little bit ad hoc here. Okay, I'm not giving you the solution here. If you like this, you can do it yourself. I just told you that you should not use it, and I make the observation that you always do what I should tell you to use it, then maybe then you won't use it. So you solve 7.4, for example, for rho. Suppose you want to specify u. Then after this you use 7.5, inserting rho, yeah, for F10 and 7.2, and then the 7.3 again for F11 and F1 minus 1, and you are done. Okay. Problems of these are manifold. First thing is difficult to generalize to other orientations, in particular corners, but it's also difficult to generalize this to, I mean, it's not impossible, to other lattices, say, yeah. This is possible, and it has been done, but it requires additional information or additional assumptions, yeah. So we are fine here because we want to set, we have two velocities, one pressure, and we are missing two populations. Yeah, depending on your lattice, this could look very different. Yeah. So in corners, this doesn't work. Doesn't matter whether concave corners or convex corners. I mean, this thing is really very unstable, to the extent that it is basically unusable for these kind of simulations that you do in civil engineering. I mean, it's completely off. But still, I mean, it's in the book. Reason it's in the book is because, yes, history, I mean, it's even in the lecture now. It's in different books. And And it is also used in practice. I just noticed this recently going to the conference, so I'm not telling the truth here. It is still in use in complex fluids systems where you are studying phase transition stuff at very low Reynolds number. I mean, this is completely legit research, yeah. But and in this part of the world, this works. But since we are in a civil engineering department, we have different applications in mind. For example, wind parks, and there you cannot use this. Also, now see, okay, I'm out of time, but we now come to the link-based boundary conditions. So, now bashing the past, we were talking that this to people in the past appeared to be a very natural thing, to put boundaries on the nodes, yeah? Now, when you follow our analysis, which I would claim is a little bit more modern, I mean more modern than from the 90s, yeah? Nowadays we are using this in-between time step thing a lot, yeah? So we notice we are actually solving the equation not for the pre-collision part as is here done in the Saussure boundary condition, and not for the post-collision part, but for the average between before and after collision, yeah? So the equation that we solve, or the variables that we solve for, they don't exist on the nodes, and they don't exist at the time steps. They exist in between the nodes and in between the time steps. Yeah? So actually, for the Lattice Boltzmann method, it's much more natural to put things in between the nodes, to put a boundary condition in between the node and let it work on the link. And this is the boundary conditions that are actually in use. Okay, let's draw our diagram again. So we have nodes, say like this, and I'm not going to draw all the populations now. Say this here would be the nodes inside the wall here. So we would have a population that is going here, something is happening in the boundary, and then something is coming from the boundary to here. Yeah, and this thing here is we call this Fi, and this is after collision, and the other one is F minus I, so I with this bar on top, and this will become the pre-collision, yeah, at the nodes at this position N, say here, right, if we call this N. So, now we place the boundary condition halfway between nodes. And the simplest case of this is the halfway bounce back. And whenever I say halfway bounce back, I have to acknowledge that there is, if you look at this in very detail in asymptotic analysis, you see that there is a small offset due to the stress that makes it not completely halfway. However, this offset is only of concern if the viscosity is very high, which again, we are in civil engineering, yeah, we have high Reynolds number, our viscosity is usually very small, so that for us, this is halfway bounce back. Even though, in theory, if you have a very high viscosity, this may be a little bit off. Yeah? This is not the concern in civil engineering. So halfway bounce back works by mirroring the outgoing population in flight. So, meaning Fi, so this is the one that's coming in, yeah, at the position, so I said this is xn, yeah, so the position at the next to the boundary, yeah. So it's not on the boundary, the node is not on the boundary is not on the node. Xn, the neighbor of the boundary, at the next time step receives the post-collision state from itself at the previous time step. So what this does is it produces a velocity zero boundary condition, which we call a no-slip. No-slip. So this is velocity is equal to 0 in both directions. No penetration and no penetration and sticking. Yeah, so velocity at the boundary is 0. Again, this is not what we use in practice. What we use in practice, I mean, this is used in practice, but there actually is something better, or you can try out whether this makes a difference for you. There's something called delayed bounce back. So what is that? Xt. Okay, I am running a little bit out of space, so I make this a bit more compact. Say, here would be the boundary. The boundary, here's the wall. So let me take this other color. So what we previously had was population is going to the wall and is returning back at once. So what we do now is we let the population going inside the boundary and then return it one time step later. That's all the difference. Okay? Now, guys, have you heard about this difference, or is this new to you? Yeah. It's new, okay. It's a good thing that you actually come here and learn something new. I mean, due to the time, I will not analyze this, because this is, if you are interested, yeah, you can also run your own simulation. The thing is, Lattice Boltzmann, okay, very, very, very quickly. Lattice Boltzmann has unfortunately the tendency sometimes to produce lattice scale oscillations. Yeah? Things that oscillate with one time step, up and down, up and down, up and down. Yeah, well, this can happen. And actually, the interesting thing is, even though this may happen in second moments, because it is what we call checkerboarding, so it's every second node has this, and because we use only first derivatives, yeah, the discretization is immune against these oscillations. So if the second moment oscillates, yeah, and the gradient, the gradient is actually wrong, but you don't see that it is wrong because the oscillation is filtered out by the stencil. Yeah? So problem is, if you return this directly, the population directly, you're breaking this behavior that there's always one node in between. So what you can do instead, you just wait for one more time step, and then they are again in sync. So the problem with this immediate bounce back is that they may put oscillations that may be there into your first order moments, and you see that everything is starting to oscillate and everything crashes. Again, I'm talking here from the perspective of somebody who is interested in running things with very, very high Reynolds number, right? Yeah. So this may not be of concern to you if you are again here concerned with low Reynolds number flow, but in high Reynolds number flow, this is a concern. So you have this delay. This eliminates these fast oscillations, and therefore this is much more stable. And this is not explained in the book, I'm very sure. I always have to apologize because I did not read the book, so maybe I'm speaking nonsense, but I think this is not their concern. Okay. You can try it out. Velocity bounce back. Bounce back is for setting a velocity zero boundary condition. We can generalize this to a given velocity. Generalization of bounce back. You see, bounce back in Lattice Boltzmann is a name. This is why I write this in capital. F. So the incoming population at the position x, t plus delta t, is Fi after collision at the same space. So what you do, I mean, if you mirror the population, then you get the velocity in this direction, you turn it around, and then it cancels out. Yeah. So if you want to have a velocity in this place, you have to edit, and you have to edit twice. This is why we have here 2. Here now comes something like the weight. So this is the theta, the temperature, times the lattice weights times the direction vector of the direction, not vector, the direction vector of the link times the velocity vector on the boundary that you want to specify, yeah, with theta being equal to 1/3 and Wi being the lattice weights. Lattice weights by direction, because Okay, so this is how you build a velocity boundary condition. I'm not going to explain this in detail because I have something more interesting to tell, and this is the off-lattice. I mean, of course, unless you have a question, yeah? Off-lattice boundary conditions. And these are the ways out of, say, ways out of Lego land. So we have the problem in Lattice Boltzmann that we are on a Cartesian grid, and then there are people who think about boundary conditions on nodes, and then there are people who think about boundary conditions halfway in between nodes, yeah, and we actually want to have our boundary conditions somewhere, anywhere, yeah. And this was first, I believe it was first done by, of course, using interpolation. Interpolation bounce back, done by Busidi. In 2001. So this is more modern than, a little bit more modern than, have you been alive in 2001? Yes. Okay. Recently I asked, sorry for this, but recently I asked the students whether they know a floppy disk. Do you know a floppy disk? Yeah, so this plastic things that you put into your computer where you have 1 and 4 megabytes. They had to Google this. They were sitting here in your place in the lecture. They had to Google what is a floppy disk. Is this something like a CD? Yeah, actually CDs are older than floppy disks, but this is something that they still knew. Okay, this makes me feel extremely old. So, the thing that Busidi introduced as a concept is the subgrid distance. Subgrid distance Q. So, and Q, I mean, even though we call it a distance, it's not really a distance, it's a fraction of a distance. Q is the fraction of EI delta x between the last grid node and the wall. Okay, so this is important because otherwise you would say, wait, when the link goes in a diagonal, it is longer, right? It's more than delta x, but it is the fraction of this length. Yeah. So in practice, this thing is always in between 0 and 1. Okay, now Busidi distinguished two cases. Is distinguished between Q is smaller than 1/2 and Q is larger and or equal than 1/2. Actually, the 1/2 case is the same, so it doesn't matter. Characteristic diagram. Okay, now I have to get this right because it's yeah, so we start with the Q is smaller than 1/2. So what does this mean? We have Q is smaller than 1/2 means that the wall is closer than half of the grid spacing to the wall. That the node is closer than half a grid spacing to the wall. Right, so this here is the length Q delta X. And say this here is the next time step. So what then happens? So usually, okay, I think I can do this like this. So this population that would arrive in the next time step at this node would arrive there from this location here, right? And actually, now in this case, you can actually see and believe that this distance here is 2Q delta X. Yeah? So this is, and obviously then, now what Busidi did is he would use the post-collision distributions from these two nodes and interpolate them to this location and do the bounce back with this, okay? So this looks like this, is F minus I, so next time step, T plus delta T is equal to, now we do this this linear interpolation. He also had a quadratic interpolation, but you can interpolate with using more nodes, getting higher order, but it didn't make a big difference, and we also know now why. 2Q times F star xn t. So this is at the. This here is xn. No, sorry. This here is xn. This is xn. Plus 1 minus 2q times, so it doesn't fit here, f star, wait, this is I, xn minus delta x ei, so from the neighbor, could also just say this is the neighbor, and t. So, okay, sorry for not fitting this in one line. Yeah, so this is how you can interpolate this, provided that q is smaller than 1/2. Now the problem is if q is larger than 1/2, what would happen? So if you put this line to here, say no, here is not. Then and we go up, we would get outside these two nodes, and we would have to extrapolate and not interpolate. In extrapolation, well, we cannot be sure. It may work actually, but usually it's not stable. Yeah. So then, for the q is larger or equal to 0.5, he proposed something else. X and t. Okay, let's put it this way. So, yeah. No, I need one more. So let's say the wall is now here. Now in this case he proposed to do something different. say we take this going here and this coming then here. So, I mean, previously he was interpolating the last time step, the post-collision of the last time step, yeah? Now we are trying to interpolate between the pre-collision at the next time step. Yeah, so this guy ends up here, and the one that goes the other way ends up here. And the distance, let me see that I'm not messing up. So this distance here is of course delta x, and this distance here is 2q minus 1 delta x. And now I'm going to interpolate between these. Of course, the incoming populations there are the outgoing populations up there, right?
The incoming populations there, yes.
Yeah, so then I can write this in terms of post-collision populations. Xn t is equal to 1 over, so the complete distance here is delta x plus 2 delta x minus 1. So it is 2 delta x. Fi, again, this is a linear interpolation. Xn and t plus 2q minus 1. This is the other distance. It's the, what's called it, I don't know. It's Fi asterisk. This is just a linear interpolation, yeah? There's a word for this, I've forgotten. Right. So this is the other case. This case is actually interesting in so far as this uses the populations only on that node. Yeah, so there's no neighbor involved in this. Yeah, up there we unfortunately have to use a neighbor in addition. Yeah, and there may be some problems with this. For example, if you're in a corner, the neighbor may not be there. Yeah, and I mean, dealing with neighbors is always a problem because you have to pick up your neighbor, have you updated your neighbor, and so on. Yeah, for this reason, what has become more popular in the past, and I do this on a new page, is the one-point boundary conditions, one-point interpolated. So, and there are 24 of people in the world who claim that they have invented this. And there are slight variations on this, but they all work. In the end, they all work in a similar way. And let's just look at one example out of this. So say these are again our nodes here. So for this boundary condition, we use only one version. So we don't care whether Q is larger or equal, larger or smaller than 1/2. Okay, when you look in the book or in the paper of Bosidi, they will never draw the illustrations of their boundary conditions in this diagram. Yeah, so because they don't need this, they're interpolating only in space. Yeah, they either interpolate at this time in space, so at the previous time step, or they interpolate at the coming time step in space, but they always interpolate in space. The idea behind this one-step bounce back is that you interpolate in space and time, and there we need this kind of diagram. Yeah, so the thing is now the following. We see that this population would end up here, and this population would end up here. So what we do is we do a bounce back. So say this, we call this here, okay, we call this XBC, and we will call this here XA, and this here is what we call XN. Now here we can do a bounce back, which is just turning this population around, and then we could interpolate in space and time to this location here. Yeah? And then when you remember me saying that we should actually do a delay, which is not very accurate in time, you can already notice, okay, we can use a little delay here, yeah, and just keep this here going down, and then we have a very nice boundary condition, yeah, interpolated in space and time. Yeah, that requires only the populations in one node, and there's nothing that requires the distance to be in a particular setting. So okay, let's go through this, and this will be the finishing of today, which. Okay, I remind you, officially we have 3 hours here. So linear interpolation. So this year I'm actually doing my 3 hours. Linear interpolation along a characteristic. So this line here in space and time we call a characteristic. So what we first do is we get to this again is Fi, and this again is F minus I. Yeah? So we go to Fi at the location of the boundary and at the time t plus q delta t. I mean, because you see, this here, this is linear all, this is also q, this is q delta t, yeah? This up here is q delta x, and this is q delta t, yeah? So, at time t plus q delta t is Fi, so how do we get there? We get there by seeing that we have a pre-collision population up there, and we would have a pre-collision population down here. Yeah? So we need to use linear interpolation, 1 minus q, with this plus Fi x. We have to give this a name, so I call this, I don't know, in the volume, xv. Okay, I call it xv. I don't know why. Xv t plus delta t. So at the next time step, this will be the incoming population, and this will multiply by q. So this will be the linear interpolation between these two. So what is this ominous Fi xv t plus delta t? So very obviously, this is, because it's the incoming population, it is equal to the outgoing population at the node itself at the previous time step. Yeah? So with this, we have arrived at the boundary. Sorry, I forgot the post-collision. Yeah? So now we are at the boundary. And now bounce back at the wall. Okay, I've written the same equation. Okay, now I know what I wanted to say. Yes, so if I x b c, just do it again. T plus q delta t is equal to fi x n t 1 minus q plus fi after collision, so 1 before collision, 1 after collision, xn and t times q. So, okay, same time, same space, same place, just once before collision and once after collision. Then we do the bounce back on the wall, which just means we are returning this population. Incoming is outgoing. Bounce back on the wall, meaning, okay, it's again the same thing. The only thing is now from I, it goes to minus I at the boundary condition at t plus q delta t is equal to, and this is now, of course, exactly the same. Sorry for all the writing. 1 minus q plus fi after collision x n t times q. So what we actually want to know is fi of xn, f minus I of xn incoming, yeah, at t plus delta t. Yeah, this is what we want to know. So what we are doing now is we are, sorry for going back to the picture, we now have a population. Yeah, we could actually draw this as, so this, because it's doing bounce back, it's coming back here, yeah, and we want to interpolate this together with this guy. So we interpolate we do another interpolation between fi at xa, so this is the neighbor t plus delta t, and fi x bc at t plus q delta t. So, interpolation in space and time, we interpolate to the position fi xn. So the complete distance between them is q plus 1. Yeah, so because on one side we have q and on the other side we have distance 1. So this distance here is q, this is q, and this is 1. So the entire distance between the two is q plus 1, right? So this leads to t plus q delta t is q plus 1 plus q delta t q plus 1. So this is where the time is going. This is xa, the one on the left in this picture, t plus delta t, next time step, q divided q plus 1, plus f I minus I x bc, t plus q delta t, and also this q by q plus 1. So because okay, BC. So this guy here can of course be written as Fi x xa t plus delta t is of course the post-collision population at the node itself at time t, which means that we can write Fi at the position xn and at time t plus 2q delta t divided by q plus 1 is equal to q divided by q plus 1 f minus I x n plus t. So now let me see. We have to replace this guy here, yeah, with this guy here. We have to multiply with of course this q plus 1. And if I'm not mistaken, so I'm sorry, I'm now writing it from my script. So I hope there are no mistakes in this. 1 minus q plus 1, the pre-collision and the post-collision Fi star xn t q plus 1. So I have to admit, you can get messed up with this linear interpolations because you're using several linear interpolations. I hope I did not mess this up, but that's now would be it. And now the only thing that may be a little bit troublesome is that this here is not exactly 1 delta t, yeah? But since we use this in diffusive scaling, or since we get the Navier-Stokes equation only in diffusive scaling anyway, diffusive scaling, delta t is actually proportional to epsilon square, yeah? So whatever error in time is not important because 2q plus 1 delta t is actually, this is actually second order, and now you have to remember we are using linear interpolation, which is second order accurate. Yeah? So whatever error you do with this linear interpolation in space is of the same order as this offset in the time. Yeah? So this is why you simply don't care and say your boundary condition now is FIBC. Hopefully now it's everything right at the position x t plus delta t, which is, of course, you make a mistake here, Now this goes into Fi after collision, xn t plus Fi after collision in the other direction, f minus I and Fi, xn and t. So this goes into q plus 1 plus Fi before collision now, n t and 1 minus q and q plus 1. And this is not, okay, so this is not completely unique. You can have some variations, some small variations in this equation, yeah, because you can get the same information in different ways. So there's actually several ways of doing almost exactly the same, and they have been popping up 10 years or so ago in a lot of different formats, but they all are basically doing the same thing. So they are interpolating in space and time and just use a small offset in time in order to get it right in space, which is sufficient because the second order, a linear interpolation in space is as accurate as the next neighbor interpolation in time. Okay, yeah, thank you. I will stop the recording now.